Hey guys, here is the last section for Unit 9. It's 9.4, Unit Growth and Decay. Oops, this little box is in the way. Growth and Decay regression. So when you hear the word regression, you should think of our favorite key on the calculator in Desmos, Y1 tilde. So that's what we're going to do. We're going to find a regression to fit the table. So choosing a method, choosing a model. Our first table is physics. The table shows the amount of a radioactive element in a sample over time. So our x, our independent variable, is the days. Y is the mgs. I'm assuming that's milligrams of a radioactive element. So on day 0, there's 200 milligrams. Day 20, 179. Day 40, 160. Day 300, there's 37. Find a model that best fits our data. Step 1, make a scatter plot of the data. And in this box here, write the steps you use. So you're going to type in this box the steps we used. Guess what we're using? Desmos! So how do you make a scatter plot in Desmos? Hit the plus, hit table, type in your values. I've done that already. Here is my scatter plot. So back to here. What are the steps you used? I hit the plus key, chose table, and entered my X's and Y's. Simple explanation, guys. That's all I'm looking for. It's just my being able to check for understanding on what you guys understand and don't understand. Step 2, find the graph of a regression model to fit the data. Write the steps/equation you used. All right, here's our y1 tilde part. Looking at these, does it look like they're in a straight line? I don't know. But here, right here, I typed in the linear regression model. How do I know it's linear? There is no square on my x, and my x is not an exponent. So those are the 3 functions we've used so far. We've done linear. We have done quadratic. See, there's a square on my x, no square there. And now we're doing exponential. And from the last section, how do I know, or is it section 9, 1 or 2? How do I know it's not linear from the equation? My variable is an exponent. It's obviously not linear. All right, so here I put in the linear regression y1 tilde mx1 plus b. It hits one of my dots, points. It's above the majority of them and below 2 of them, 3 of them, because there's this one here. What do you think? Do you think that's a good model for our data? Pause the video, think about it. Here is my quadratic. Ooh, that crosses almost at my y-intercept there of that point, 0, 200. It's 1, 2, very close to most of the points. What do you think? The part I don't like about the quadratic that always bothers me is, look, it gets down to here and it's assuming my function's going to go back up. Is my function going to go back up? Well, it's this radioactive element sample. If you know anything about radioactive materials, I know there used to be a video game called Half-Life or something like that because my son used to play it. Radioactive materials decay and they don't come back. They're not going to all of a sudden start to reproduce and go back up. And then here is my exponential. Bam. That one looks about spot on. It goes through every single point. So my guess is it's going to be the exponential one. Now back to my question. What steps / equation was used? Find a graph, a regression model to fit the data. So let's see. I typed in y1 tilde for the linear, quadratic, and exponential functions. It seems that the exponential one went through the most points. Old quadratic there. All right. Now, I know I talked about this in one of my other videos. If you bothered to watch some of my other videos, the R2 value. And we talked about this when we did regressions before, the R squared. R squared for the linear is 0.95. The R squared for the quadratic is 0.99999. I got to say, that's pretty spot on. The R square value for my exponential is exactly 1. So in the absence of putting in the exponential one, I would have gone with the quadratic one because 0.99999 is pretty spot on. But since it was a real world situation and what my knowledge of radioactive materials, I know radioactive materials decay. They don't start to ramp back up again. So you look at your R2 value, the closer it is to 1, the better it is, the better of prediction the function is. And given my 3 choices here, without even worrying about what the graphs look like, going off the R squared values, the exponential one is obviously the best choice. So let's go ahead and put this in here. The R squared value for the exponential function was exactly 1. That tells us that is it. That is it. That is our function. You can't get any closer to 1 without being 1. All right, B. Use your model to predict how many milligrams of the element there will be in 450 days. Let's go back to Desmos. 450 days. Now there's 2 things I can do. I can go ahead and add 450 to my chart. No, that's not going to work. Forget I said that. How about we graph x equals 450. You can tell what this point's going to be, but it's hugging so close to... Oh, no, actually, that one's not too bad. I did one earlier like that, and it was so close to the y-axis that it wouldn't differentiate it from 0. It wasn't telling me all the decimal points. But right here, when x is 450, how much do I have left? I have about 16 milligrams left using our function. The other way you could have done it, see right here, it gave me my A value and my B value. You could have substituted in your x and done it algebraically, but there was no need to do that because we had it graphed already. So back over here, I used my model to predict, and it was 16 milligrams. So you type that in the box here. There will be about 16 milligrams left after 450 days. Perfect. Good job.